The universe is expanding faster than we can understand it. At the very edge of everything we can see lies a wall of pure mystery, a cosmic horizon that hides the answers to our deepest questions. We are about to journey beyond that wall, exploring 25 of the most profound enigmas in all of existence. By the end of this exploration, you will grasp the fundamental puzzles that define modern cosmology and our place within the cosmos. We will confront the strange force ripping space apart and investigate the silent, invisible substance that holds galaxies together. This is a voyage to the limits of human knowledge, where each mystery solved reveals 10 more waiting in the dark. What do you believe lies beyond the edge of everything we know? The first and perhaps greatest of these mysteries begins with a discovery that shattered our cosmic expectations. For decades, scientists believed the universe's expansion, born from the Big Bang, was gradually slowing down over time. The collective gravity of all the galaxies, stars, and matter was thought to be acting like a cosmic brake, pulling everything back together. Then, in the late 1990s, two independent teams of astronomers made a startling observation. By studying the light from incredibly distant stellar explosions called Type 1, a supernova, they measured how fast the universe was expanding at different points in its history. They expected to see the slowdown. Instead, they saw the opposite. The data revealed that the expansion of the universe is not slowing down at all. It is speeding up. Something is actively pushing space itself apart, and we have no idea what it is. We call this something dark energy. Dark energy is not a substance you can touch or see. It is best understood as a property of empty space itself. Think of the vacuum of space not as a true nothingness, but as a seething, bubbling sea of potential. Quantum physics tells us that even in a perfect vacuum, pairs of virtual particles constantly wink in and out of existence. This activity should give the vacuum an inherent energy, a pressure that permeates every cubic centimeter of the cosmos. When Einstein was formulating his theory of general relativity, he introduced a fudge factor into his equations to keep the universe static, which he called the cosmological constant. He later called it his greatest blunder when the expansion of the universe was discovered. Now, it seems he may have been right for the wrong reason. The cosmological constant is the leading candidate for dark energy, representing this innate energy of the vacuum. But here lies the heart of the mystery, a problem so severe it is often called the worst theoretical prediction in the history of physics. When physicists calculate how much energy this quantum vacuum should have based on our best theories, the number they get is absurd. It is off by a factor of 1 followed by 120 zeros. That is not a small error. It is a number so incomprehensibly large that if this predicted vacuum energy were real, the universe would have torn itself to shreds in an instant after the Big Bang. The actual dark energy we observe is incredibly weak, yet over the vast emptiness of cosmic space, its gentle, repulsive push adds up, overwhelming the pull of gravity on the largest scales. Why is the observed value of dark energy so unimaginably tiny compared to the theoretical prediction? This is the vacuum energy problem, and solving it may require a revolution in physics. Some scientists propose that dark energy is not a constant at all, but a dynamic field that changes over time, which they call quintessence. Others suggest modifications to Einstein's theory of gravity itself. The true nature of dark energy dictates the ultimate fate of everything. If it remains constant, the acceleration will continue forever, leading to a cold, dark, and lonely end where galaxies are ripped apart. If it strengthens, it could result in a catastrophic Big Rip, tearing apart atoms themselves. This first mystery is the foundation of our cosmic horizon. It is the force actively shaping the future of reality, and we are only just beginning to sense its shadow. But if dark energy is the force pushing the cosmos apart, what is holding it together? The evidence points to a second, even more pervasive phantom. Look at a spiral galaxy like our own Milky Way. The stars on its outer edges orbit the galactic center at tremendous speeds. According to the laws of gravity, these high speeds should require an immense amount of mass in the galaxy's core to keep those stars from flying off into the void. But when we add up all the visible matter, the stars, the glowing gas, the planets, the numbers do not come close. There is simply not enough gravity from what we can see to explain the motion we observe. This discrepancy, first noted by astronomer Vera Rubin in the 1970s, is our first major clue. The stars are orbiting as if the galaxy is embedded in a vast, invisible sphere of something heavy, something that does not emit or reflect light. We call this something dark matter. The evidence goes far beyond spinning galaxies. We can see its gravitational handiwork in the way massive clusters of galaxies bend the light from objects behind them, a phenomenon called gravitational lensing. The amount of bending is so extreme that it requires far more mass than the visible galaxies in the cluster provide. Dark matter acts as the cosmic scaffolding upon which the visible universe is built. In the early universe, its gravity drew ordinary matter together, allowing the first galaxies to form. Without it, our cosmos would be a formless, starless haze. We know it exists because of its overwhelming gravitational influence, which accounts for roughly 85% of all the matter in the universe. Yet after decades of searching, we have no idea what it is made of. The leading idea is that dark matter consists of an entirely new class of particle, one that interacts with ordinary matter almost exclusively through gravity. The prime candidate for decades has been the WIMP, which stands for Weakly Interacting Massive Particle. As the name suggests, these hypothetical particles would have mass and interact only through the weak nuclear force and gravity, making them incredibly difficult to detect. Experiments deep underground, shielded from cosmic rays, have spent years waiting for the faintest bump from a WIMP colliding with an atomic nucleus. So far, the detectors have remained silent. Another intriguing candidate is the action, a particle originally proposed to solve a different puzzle in particle physics. Actions would be incredibly light, potentially streaming through space in vast numbers like a ghostly wind. New experiments are now searching for the subtle way actions might convert into photons in the presence of a strong magnetic field. The persistent failure to directly detect any dark matter particle has led some scientists to propose a radical alternative. What if there is no dark matter at all? What if, instead, our understanding of gravity is incomplete on the vast scales of galaxies? This idea is known as modified Newtonian dynamics, or MIN. It suggests that gravity behaves differently when it becomes extremely weak, such as at the edges of galaxies, creating the illusion of extra mass. While MIN can explain some galactic rotation curves surprisingly well, it struggles to account for all the evidence from galaxy clusters and the large-scale structure of the universe without still invoking some form of unseen matter. The debate is fierce, highlighting a profound truth. Dark matter is not just a missing ingredient. It is a symptom of a potential crack in our foundational theories of physics. We are left with a universe where most of the material substance is completely invisible to us, a silent partner in the cosmic dance, whose identity remains one of the most frustrating and enduring mysteries on the horizon. That silent, invisible substance holding galaxies together forces us to confront a deeper question about the nature of life in a cosmos so vast. The universe is staggeringly old and unimaginably large, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars host planets, and a significant fraction of those planets likely exist in habitable zones where liquid water could exist. Given these numbers, the emergence of life elsewhere seems almost a mathematical certainty. And if life emerges, intelligent, tool-building civilizations could have had billions of years to arise, spread, and fill the galaxy. This simple logic leads to the famous question first posed by physicist Enrico Fermi during a casual lunch conversation in 1950. If they are out there, where is everybody? This is the Fermi paradox, the profound contradiction between the high probability of extraterrestrial civilizations and the total lack of any evidence for them. We see no signals, no artifacts, no visitors. The cosmos, for all its grandeur, appears utterly silent. This silence is deafening, and it suggests something is terribly wrong with our assumptions. One of the most unsettling explanations is known as the Great Filter. The idea is that the evolution of life from simple chemistry to a spacefaring civilization requires passing through a series of incredibly difficult steps, like a cosmic obstacle course. Perhaps one of these steps is so improbable that it acts as a near impenetrable barrier, a filter that almost every potential civilization fails to pass. The terrifying question is, where is this filter located? Is it behind us? Were we miraculously lucky to evolve complex life, or for intelligence to emerge at all? If so, we might truly be alone, a rare spark in an endless dark. Or, more frighteningly, is the great filter still ahead of us? Perhaps every civilization that reaches our level of technological development inevitably discovers some technology or succumbs to some flaw that leads to its own destruction. Nuclear war, runaway artificial intelligence, engineered pandemics, or ecological collapse could be the universal fate of intelligent species. Our current silence would then be a grim omen, a warning that no one makes it past this point. Other solutions are less dire but equally mind-bending. The zoo hypothesis suggests that advanced civilizations are aware of us, but have chosen to place our region of the galaxy under a kind of observational quarantine. They are watching, waiting for us to reach a certain level of maturity or technological harmony before making contact, much like we observe animals in a wildlife preserve without interfering. Alternatively, the universe might be teeming with life, but we are simply not listening correctly, or their methods of communication are so advanced they are indistinguishable from natural phenomena to our primitive instruments. Perhaps interstellar travel is simply too difficult, or the vast distances of space and time make galactic civilizations impractical. Every star system could be an isolated island, its inhabitants destined to gaze at the ocean of stars without ever sailing it. The implications of this mystery are not merely academic. They shape our understanding of humanity's future and our place in the cosmos. If we are alone, we bear an immense responsibility as the universe's only known custodians of consciousness. If we are not alone, but the filter is ahead, our every action takes on a desperate urgency to survive our own adolescence. And if we are being observed, our every achievement and failure is part of a cosmic test we do not yet understand. The great silence is not an empty void, but a mirror reflecting our deepest hopes and fears back at us. The profound silence of the cosmos makes every unexpected signal from our own probes feel like a shout. In the vast emptiness between the stars, two human-made objects began telling a strange story. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, were pioneers in the truest sense. After completing their missions to Jupiter and Saturn, they continued on trajectories that would eventually carry them out of our solar system entirely. As they sailed into the dark, scientists tracking their radio signals noticed something bizarre. Both spacecraft were slowing down slightly more than anyone had predicted. This tiny, persistent deceleration became known as the Pioneer anomaly. It was a minuscule effect, equivalent to a 10 billionth of the gravity you feel standing on Earth. But over the vast distances of space, even this tiny push added up to a navigational puzzle. For years, this unexplained deceleration hovered at the edge of physics, a tantalizing hint that our understanding of gravity might be breaking down at the frontier of our own cosmic neighborhood. Some researchers wondered if it was evidence for modified gravity theories, like the ones proposed for dark matter. Others speculated about the influence of unseen dark matter in our solar system, or even the subtle drag of the interstellar medium. The Pioneer anomaly became a classic space mystery, a ghost in the machine that seemed to whisper of new physics just beyond our reach. Then came the painstaking detective work. A team of scientists led by Slava Turyshev spent years recovering old telemetry data from the spacecraft, some of it stored on outdated magnetic tapes and even older printouts. They built a detailed thermal model of the Pioneers, accounting for every watt of heat generated by their radioactive power sources. What they discovered was a masterclass in humility. The anomalous deceleration was not a new force of nature. It was, almost certainly, the spacecraft pushing back on themselves. The heat from the Pioneer's electrical systems and plutonium power units was radiating away from the craft unevenly. A little more heat was emitted from the back of the dish-shaped antenna than from the front. This tiny imbalance created a net pressure, a gentle photon push that acted as a constant, very slight break. It was thermal radiation pressure, a well-understood phenomenon, acting in a way no one had fully accounted for in the original trajectory calculations. The mystery that had fueled speculation for decades was solved not by a revolutionary theory, but by meticulous engineering. Yet, the legacy of the Pioneer anomaly is far more than a cautionary tale about accounting for heat. It demonstrated how the deepest mysteries can sometimes have the most ordinary explanations, hiding in plain sight within the complex reality of our own technology. More importantly, it showed how a single, stubborn data point can ignite the scientific imagination, forcing us to question our most fundamental assumptions. While the specific case was closed, the door it opened remains ajar. The anomaly fueled serious research into alternative gravity models for years, research that continues to inform our investigations into the larger mysteries of dark matter and dark energy. It stands as a permanent reminder that at the horizon of our knowledge, the line between a revolutionary discovery and a simple oversight can be vanishingly thin. Our instruments are not perfect observers. They are physical objects interacting with the universe, and sometimes the universe whispers its secrets through the creaks and groans of the vessel itself. The meticulous explanation of the Pioneer anomaly shows how mysteries can dissolve under scrutiny. Yet one signal from the void has stubbornly resisted all attempts at explanation. A haunting whisper that arrived on a late summer night in 1977. At the Big Ear Radio Telescope in Ohio, a volunteer named Jerry Amon was sifting through reams of computer printout data, a routine search for patterns in the cosmic static. His eyes scanned a column of alphanumeric codes representing signal strength, and then he saw it, a sequence of characters so startling he circled it in red pen and wrote a single, emphatic word in the margin. Wow, the wow signal, as it became known, was a 72-second burst of intense radio noise. It was not random static. It was a pure, narrowband signal at exactly 1,420 megahertz, a frequency that sits in a protected radio quiet zone, a band where earthly transmitters are forbidden to broadcast because it is a natural emission frequency of hydrogen, the most common element in the universe. It was the perfect calling card, exactly what scientists predicted an advanced civilization might use to signal its presence across the light years. The signal rose and fell in intensity over exactly 72 seconds, matching precisely the time it would take for a fixed telescope like the Big Ear to sweep a single point in the sky. This meant the source was fixed in space, not a passing satellite or aircraft. For that brief window, it was the most compelling blip of data in the history of the search for extraterrestrial intelligence. The excitement was immediate and electric, yet when astronomers pointed every available instrument back at that same spot in the constellation Sagittarius, they heard nothing. No repeat, no pattern, just the eternal silence of space. For decades, the WOW signal stood alone, a one-off event that defied natural explanation and fueled endless speculation. Then, in 2016, a scientist proposed a new, mundane answer. He suggested the signal might have been caused by a passing comet, two of which happened to be in that region of the sky at the time. The idea was that clouds of hydrogen gas surrounding the comets could have emitted the characteristic frequency as they were excited by the sun. This hypothesis was widely publicized, but it was also swiftly and fiercely contested by other astronomers. They pointed out that comets are not strong, point-like radio sources at that specific frequency, and the Big Ear telescope had observed other comets before without detecting anything remotely similar. The comet explanation for many simply did not fit the data, so the mystery endures. The WOW signal remains in a category of its own. It is the best candidate we have ever received, a signal that passed every initial test for an artificial interstellar broadcast. Yet its singular nature makes it impossible to verify. Was it a fleeting malfunction of earthly origin, a natural astrophysical phenomenon we do not yet understand, or a one-time beacon from a civilization that spoke just once into the dark? Its power lies not in an answer, but in its perfect ambiguity. It is a fossil of a moment, a scratch on the record of the cosmos that tells us something extraordinary happened, even if we may never know what. The haunting ambiguity of the WOW signal teaches us to listen carefully to the cosmic static. But what if the universe is not just whispering? What if it is screaming in bursts of energy so violent they outshine entire galaxies, yet vanish in the blink of an eye? This is the enigma of fast radio bursts. First discovered in archived data in 2007, an FRB is a flash of radio waves of almost unimaginable power. In a mere thousandth of a second, a single burst can release as much energy as our sun emits over 80 years. For over a decade after their discovery, these events were singular mysteries. Astronomers would catch a fleeting, brilliant spike in their data from a random point in the sky, and then nothing. They were like cosmic firecrackers, popping off in the dark, impossible to trace. The leading theory was that they were the death cries of catastrophic one-time events, like a neutron star collapsing into a black hole or two incredibly dense objects merging. If that were true, we would never see a signal from that same spot again. Then, in 2016, everything changed. Astronomers detected an FRB that repeated, not just once, but several times, from the same location. This single observation shattered the cataclysmic model. Whatever was producing these bursts was surviving the event. It was not a final scream, but a periodic, powerful shout. This discovery of repeating FRBs opened the floodgates. We have now detected hundreds of them, with some sources flashing repeatedly in unpredictable patterns. The hunt to pinpoint their origins became a global race. The breakthrough came when scientists used a network of telescopes to triangulate a repeating burst to its home galaxy, a small, turbulent dwarf galaxy over 3 billion light-years away. They traced it to its specific neighborhood within that galaxy, a region brimming with star formation. This pointed strongly to a natural, if extreme, astrophysical engine. The current prime suspect is a magnetar, a type of neutron star with a magnetic field 1,000 trillion times stronger than Earth's. Think of a magnetar as a city-sized atomic nucleus spinning furiously, wrapped in a magnetic field so intense it can literally twist the fabric of space-time around it. A starquake on its solid, crystalline crust, or a sudden magnetic reconnection event, could theoretically unleash a titanic shockwave, blasting out a pulse of radio waves across the cosmos. Yet, even magnetars struggle to explain the most extreme bursts, or the bizarre, sometimes periodic patterns of some repeaters. This gap in understanding leaves the door open for more exotic ideas. Some theorists suggest cosmic strings, hypothetical cracks in the fabric of the universe from its earliest moments, vibrating and snapping. Others, far more speculatively, have pondered whether we are seeing evidence of immense alien technology, like power beams for interstellar light sails, though most scientists consider this an explanation of absolute last resort. But here is the beautiful twist. Regardless of what causes them, fast radio bursts are proving to be invaluable tools. As these powerful radio waves race across billions of light-years, they pass through the diffuse clouds of gas and plasma that float in the vast voids between galaxies. This material, the universe's missing ordinary matter that had eluded our telescopes, subtly slows and scatters the radio waves. By studying the precise fingerprint of this dispersion in an FRB signal, astronomers can now weigh this invisible hot gas. These mysterious screams from the dark are becoming cosmic probes, allowing us to finally map the hidden scaffolding of the universe itself. They are both a profound question and an unexpected key. While fast radio bursts scream across the cosmos, another mystery arrived as a silent, blinking anomaly in a sea of steady starlight. It was discovered not by a radio telescope, but by the unblinking eye of NASA Kepler Space Telescope, an instrument designed to find planets by watching for the tiny, periodic dips in starlight caused by an orbiting world passing in front of its sun. In the constellation Cygnus, Kepler was observing a star cataloged as KIC 8462852, a star slightly larger and hotter than our own sun. What the data revealed was not the clean, repeating signature of a planet. It was something utterly unprecedented. The star's light would dim by staggering amounts, sometimes by just 1%, other times by a jaw-dropping 22%, and these dips were wildly irregular in both their timing and their shape. A planet, even a giant one, would only block about 1% of this star's light. To cause a 22% dimming would require an object nearly half the width of the star itself, something unimaginably huge and utterly opaque. The pattern made no sense. It looked less like an orbit and more like something was chaotically passing in front of the star in chunks. The data, made public by citizen scientists, immediately captured the world's imagination. Astronomer Tabitha Boyajian, who led the initial study, found herself at the center of a firestorm. The most tantalizing, if extreme, hypothesis came from those considering the possibilities of advanced intelligence. Could this be evidence of a Dyson sphere, a hypothetical megastructure built by a civilization to capture the entire energy output of its star? The irregular dips could be explained by a partially completed swarm of energy-collecting panels, orbiting in a chaotic, artificial cloud. The star soon bore an unofficial name, Boyajian star, or more commonly, Tabby's star. The idea of alien megastructures was intoxicating, but science demands evidence, not just excitement. The global astronomical community turned its instruments toward that one point of light, seeking more data. The key was to study how the dimming changed across different colors or wavelengths of light. A solid object, like a planet or a megastructure, would block all light equally. Dust, however, blocks blue light more than red light. As observations piled up, a clear signal emerged. The dimming was much more pronounced in blue light than in red. This was the fingerprint of dust, not solid metal or rock. The alien megastructure hypothesis, while a thrilling thought experiment, began to fade. The focus shifted to natural, if extraordinary, astrophysical explanations. The leading theory now involves a colossal swarm of disintegrating comets, or the remnants of a shattered planet or moon, creating a vast, uneven cloud of fine debris orbiting the star. Another compelling idea suggests the star might have recently consumed a giant planet, throwing its system into chaotic disarray, or that it is surrounded by a planet with a ring system so vast it would make Saturn's look like a child's toy, with gaps and clumps in the rings causing the irregular dimming. The mystery of Tabby's star is a masterclass in the scientific process. It began with a bizarre signal that defied all standard models. It sparked a legitimate, if extraordinary, hypothesis that captured the public mind. Then, through rigorous observation and analysis, the extraordinary was pared away, guiding us toward more likely, if still deeply strange, natural explanations. The story does not disappoint because the answer wasn't aliens. It enlightens because it shows how our search for the extraordinary sharpens our tools and deepens our understanding of the ordinary chaos of the cosmos. It reminds us that the universe is perfectly capable of producing wonders bizarre enough to stretch our imaginations to their breaking point, all on its own. The bizarre dimming of a distant star reminds us that cosmic objects rarely fit our neat expectations. But in October 2017, an object entered our solar system that defied all categorization, arriving from the depths of interstellar space. The Pan-STARRS telescope in Hawaii first spotted it as a faint point of light moving at blistering speed. It was named Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. Calculations of its trajectory left no doubt. This was the first confirmed object from another star system ever observed passing through our own. The excitement was immediate, but as more data trickled in, that excitement turned to profound bewilderment. Oumuamua's properties were, in a word, alien. First, its shape. By observing how its brightness changed dramatically as it tumbled, astronomers inferred it was not a roundish lump like most asteroids or comets. Instead, its light curve suggested an extremely elongated form, perhaps 10 times longer than it was wide. Imagine a cigar or a pancake tumbling chaotically through space. This was a shape rarely, if ever, seen in our own solar system. Second, it showed no visible coma, the fuzzy cloud of gas and dust that surrounds a comet as it is warmed by the sun. Spectroscopic analysis found no signs of water ice or carbon dioxide, the usual ingredients of cometary outgassing. Based on this, it was initially classified as an interstellar asteroid, a silent, inert rock. Then came the third and most puzzling clue. As Oumuamua sped away from the Sun, its trajectory was tracked with extreme precision. Scientists found it was ever so slightly accelerating, deviating from a path dictated purely by the Sun's gravity. This non-gravitational acceleration is common for comets, as jets of vaporizing ice act like tiny rocket engines. But Oumuamua showed no visible jets, no dust tail, no coma. Something was pushing it, but we could not see what. This trifecta of strangeness, the extreme shape, the lack of a coma, and the hidden acceleration ignited a fierce scientific debate. The most controversial explanation came from Harvard astronomer Dr. Avi Loeb. He proposed that Oumuamua's properties were consistent with a thin, lightweight object pushed by the pressure of sunlight itself, a technology humans are beginning to explore called a light sail. He suggested it could be a piece of discarded alien technology, a derelict probe or a fragment of a larger structure, drifting through the galaxy. The idea captured global headlines, framing Oumuamua as a potential artifact from another civilization. The mainstream scientific community, while fascinated by the mystery, leaned toward natural explanations that stretched our understanding of planetary formation. One compelling theory, developed after Oumuamua had already departed, focused on the outgassing of hydrogen ice. Hydrogen is the most common element in the universe, but it is very difficult to detect with our telescopes, especially in the thin amounts Oumuamua might have released. A body composed largely of hydrogen ice could have experienced subtle, invisible outgassing as it passed near the Sun, providing the thrust for its acceleration without producing a visible dust cloud. Another theory suggested it was a shard from a Pluto-like planet torn apart by its star's gravity, a fragment of nitrogen ice that would have similar properties. The profound frustration and the core of this mystery is that Oumuamua departed our neighborhood before we could point our most powerful instruments at it. By the time we realized how truly peculiar it was already a faint speck receding into the void, too distant for detailed study. We were left with a handful of data points and a universe of questions. Was it a bizarre, pancake-shaped comet made of exotic ices, a type of object our models never predicted? Or was it, as Loeb passionately argues, evidence that we are not alone, and that our first interstellar visitor was a piece of someone else's technology? Oumuamua did not give us answers. It gave us a tantalizing, unresolved riddle, a single data point from the galactic ocean that tells us the universe is capable of producing wonders we have not yet begun to imagine. Its silent passage challenges us to build better telescopes, to watch the sky more closely, and to prepare for the next messenger from the dark. Oumuamua's silent passage leaves us with questions about the very building blocks of the cosmos. To find answers, we must rewind time to the universe's explosive birth. In the first 3 minutes after the Big Bang, the entire cosmos was a seething nuclear furnace, hot and dense enough to fuse the first atomic nuclei. This brief, violent epoch is called Big Bang nucleosynthesis. During this flash of creation, protons and neutrons collided to form the lightest elements: hydrogen, helium, and trace amounts of lithium. For decades, cosmologists have used our precise knowledge of particle physics to calculate exactly how much of each element should have been forged in that primordial fire. The predictions for hydrogen and helium match what we observe in the oldest stars and pristine gas clouds with spectacular accuracy, a triumph that confirms our basic picture of the Big Bang. But for lithium, the numbers are catastrophically wrong. The universe should contain about 3 times more lithium than we actually see. This is the cosmic lithium problem, a stubborn mismatch between our most successful theory and the observed cosmos. Think of it like a meticulous recipe for the universe's first soup. We know the ingredients, the temperature, and the cooking time perfectly. The amounts of hydrogen and helium that come out of the pot are exactly right. But the dash of lithium we expect to find is mysteriously absent. Where did it go? This is not a small error. It points to a gap in our understanding of physics during the universe's infancy. One possibility is that our models of those first few minutes are incomplete. Perhaps unknown particles, like certain types of dark matter, were present and interacted with the primordial plasma, altering the nuclear reactions just enough to suppress lithium production. Another line of thought looks not at creation, but at destruction. Maybe the lithium was made as predicted, but something destroyed it later. Old stars, the cosmic fossils we use to measure primordial abundances, are complex engines. Astronomers have proposed that processes inside these ancient stars could have gradually burned up their lithium over billions of years. Turbulent mixing might have dragged surface lithium down into hotter interior layers where nuclear fusion would destroy it. Yet, detailed stellar models have so far struggled to explain the full magnitude of the discrepancy. The lithium problem forces us to confront a humbling reality. Our story of the universe's first moments is exquisitely precise, yet it clearly misses a crucial page. Solving this mystery could reveal new physics from the dawn of time or unlock hidden processes within the hearts of the oldest stars. It is a fundamental puzzle, a single elemental mismatch that whispers of secrets still hidden within the blueprint of creation itself. That missing lithium hints at a flaw in our earliest cosmic recipe, but another mystery suggests the universe itself might be lopsided. The cosmic microwave background is the oldest light we can see, a faint, cold glow that fills every direction in space. It is the afterglow of the Big Bang, released when the universe was just 381 years old, a baby picture of the cosmos. According to our fundamental theories, this background should be almost perfectly smooth and uniform, with only tiny, random fluctuations that would later seed the growth of galaxies. This assumption is called the cosmological principle, the idea that on the largest scales, the universe looks the same in every direction, with no special place or orientation. But when scientists created exquisitely detailed maps of this cosmic afterglow using satellites like WMAP and Planck, they found something unsettling. There appears to be a strange alignment, a correlation between the hot and cold spots in this ancient light and the plane of our own solar system. This unexpected pattern has been dramatically nicknamed the axis of evil. It is as if the universe's oldest fingerprint is somehow oriented along the same general plane as Earth and the other planets orbiting the Sun. This should be impossible. The cosmic microwave background comes from a time long before our solar system, or even our galaxy, existed. Its patterns should have no connection whatsoever to our local modern neighborhood. Finding one is like discovering that the cracks in a 300-year-old painting perfectly line up with the floorboards in your living room. The coincidence is staggering, and it points to one of two deeply troubling possibilities. First, it could be an unknown local effect, a subtle contamination in our data, perhaps dust in our own solar system, or even the magnetic field of our galaxy is imprinting a faint signal that we have not yet fully accounted for. Scientists have searched tirelessly for such a systematic error, but so far, none has been found that can fully erase the alignment. The second possibility is far more profound. If the alignment is real, it challenges the cosmological principle itself. It would mean the universe is not isotropic, not the same in all directions on the largest scales. There would be a preferred axis, a cosmic orientation that imprinted itself on the fabric of reality at the moment of creation. This could be a relic from a time before the Big Bang, a scar from a collision with another universe in a multiverse, or evidence of a rotating universe. Some theorists suggest it might be a sign that our universe is finite and has a complex, donut-like shape, a topology that would create repeating patterns on the sky. The implications are immense. Our entire standard model of cosmology is built upon the foundation of a uniform, isotropic universe. If that foundation has a crack, many of our calculations about dark energy, dark matter, and the ultimate fate of everything could be subtly or drastically wrong. The axis of evil remains a controversial and unresolved anomaly. For some scientists, it is a statistical fluke that will disappear with better data. For others, it is the most tantalizing clue we have that our universe has a hidden architecture, a grand design we are only just beginning to glimpse. It whispers that our place in the cosmos might not be random, but somehow written into the oldest light there is. If the universe has a preferred axis, perhaps its very expansion is not as uniform as we believed. This brings us to a modern crisis in cosmology, a conflict of measurements so severe it is called the Hubble tension. At its heart is a simple question with a maddeningly complex answer. How fast is the universe expanding right now? We call this number the Hubble constant. For decades, astronomers have refined two primary methods to pin down this critical value, and they have grown astonishingly precise. The problem is, they no longer agree. The first method looks back to the infant universe. By studying the detailed patterns in the cosmic microwave background with satellites like Planck, scientists can work out the ingredients of the early cosmos, the amounts of dark matter, dark energy, and ordinary matter. Plugging these numbers into our standard model of cosmology allows them to calculate how the universe should have evolved and expanded over 13.8 billion years to reach its current size. This gives us a predicted expansion rate. The second method measures the universe directly in our own cosmic neighborhood. Astronomers use pulsating stars called Cepheid variables and cataclysmic supernova as standard candles. By knowing their true intrinsic brightness and measuring how dim they appear, we can calculate their distance with great accuracy. Combining this with measurements of how fast those galaxies are moving away from us gives us a direct, observed expansion rate. Each method, on its own, is a triumph of modern science, but they are telling two different stories. The Planck measurement from the early universe suggests a slower, more sedate expansion rate. The local measurements from supernova and Cepheids insist the universe is expanding faster, by a significant margin. The difference is not a small blip or a statistical fluke. With our current data, the probability that this discrepancy is just an unlucky coincidence is less than 1 in a million. This is a genuine tension, a crack in the foundation of our understanding. So what could be causing it? One compelling idea is that our standard model is missing a piece. Perhaps dark energy, the force accelerating the expansion, is not constant. Maybe it was stronger or weaker in the universe's adolescence, changing the expansion history in a way our current models do not account for. Theorists call this early dark energy, a temporary surge that could have tweaked the early universe just enough to explain the mismatch. Another possibility involves ghostly particles called neutrinos. We know neutrinos have a tiny mass, but what if some types are heavier than we think, or if there are more sterile neutrinos that barely interact with anything? These particles would have flooded the early universe, subtly altering how sound waves propagated through the primordial plasma, which in turn would change the patterns we see in the cosmic microwave background. There are even more exotic suggestions, like the idea that dark matter interacts with itself in unknown ways. The implications are profound. The Hubble tension is not just an academic disagreement about a number. It is a direct challenge to the lambda cold dark matter model, our best and most successful description of the cosmos. This model has passed every major test for decades. Yet now, its prediction for the universe's current expansion rate appears to be wrong. This means we might be on the verge of discovering something entirely new about the fundamental forces or particles that have shaped cosmic history. We are forced to ask, is our measurement flawed, or is our universe more strange and dynamic than our standard story allows? Our disagreement over the universe's expansion rate forces us to ask a more basic question. What exactly is the universe made of? We have dark energy, we have dark matter. But what about the ordinary stuff, the atoms that build stars, planets, and life itself? This brings us to a surprisingly personal cosmic shortfall. From our most precise measurements of the early universe, we can calculate exactly how much ordinary matter, made of protons and neutrons, should have been created in the Big Bang. Scientists call this normal matter baryonic matter. We know how much should be out there, but when we add up all the ordinary matter, we can actually see every galaxy, every star, every gas cloud, every planet. We come up short, drastically short. About half of all the atoms that should exist in the present-day universe are simply missing. This is the missing baryon problem. It is not a mystery about dark matter. This is about the very stuff you and I are made of. We are literally missing half of ourselves. So where did it all go? The leading theory paints a breathtaking picture of the universe's large-scale structure. Imagine the cosmos not as a collection of isolated galaxies floating in empty blackness, but as a vast, three-dimensional web. Galaxies and massive clusters are the dense knots where the threads of this cosmic web intersect. Stretching between these knots are unimaginably long, thin filaments of gas. These filaments are the scaffolding of the universe, and theorists have long predicted that the missing baryons are hiding there. This is not a cold, dark gas. It is a searingly hot plasma, heated to millions of degrees by the gravitational shock waves of collapsing galaxies and the energy blasts from supermassive black holes. Gas this hot does not glow in visible light. It emits energy only in very specific, high-energy wavelengths, like far ultraviolet and soft X-rays, making it nearly invisible to traditional telescopes. For years, this was just a compelling hypothesis. The missing baryons were a ghost in the equations. Then, new technology began to turn the ghost into a map. Instruments like the European Space Agency's XMM Newton telescope and NASA Chandra X-ray observatory started to detect the faint X-ray glow from the hottest parts of these filaments, especially where they connected massive galaxy clusters. But the real breakthrough came from a clever trick using nature's own flashlights. Remember the fast radio bursts, those incredibly powerful cosmic screams. As their radio waves race across the universe, they pass through this diffuse, hot gas in the cosmic web. The gas slows the radio waves down just a tiny bit, and it scatters them in a specific way, leaving a fingerprint on the signal. By studying this fingerprint from many different bursts, Astronomers have begun to weigh this invisible plasma. They are confirming that a vast reservoir of ordinary matter is indeed there, woven through the voids. The search is now accelerating. New space telescopes, like the recently launched XRISM, are designed with the specific sensitivity to see the X-ray whisper of this warm, hot intergalactic medium. Each detection is like finding a single glowing thread in a dark tapestry, slowly revealing the hidden architecture of everything. Solving the missing baryon problem does more than just balance the cosmic books. It completes our inventory of the normal universe. It tells us that the atoms we know and love are not just in the stars, but also in a magnificent, hot fog that traces the grand design of creation itself. We spent decades wondering where half of reality went, only to discover it was all around us, a faintly glowing ocean we had only just learned to see. That hot, invisible ocean of missing matter is threaded through a cosmos shaped by forces of unimaginable violence. Among the most extreme objects it contains are the universe's ultimate magnets, cosmic powerhouses that rewrite the rules of physics. These are magnetars, a rare and terrifying breed of neutron star. To understand a magnetar, you must first picture the corpse of a massive star that has died in a supernova. What remains is a neutron star, a city-sized sphere so dense that a single teaspoon of its material would weigh as much as a mountain. It is essentially a giant atomic nucleus, spinning rapidly. Now, take that already extreme object and imbue it with a magnetic field of almost incomprehensible power. A magnetar's magnetic field is a quadrillion times stronger than Earth's, and 1,000 times stronger than a typical neutron star's. If a magnetar were located halfway between the Earth and the Moon, its magnetic field would strip the data from every credit card on our planet. These fields are so intense they can literally twist the fabric of space-time around the star, a phenomenon known as frame dragging. The energy stored in this magnetic prison is astronomical, and it seeks release in cataclysmic outbursts. Magnetars experience violent starquakes, where their solid, crystalline crust, a material 10 billion times stronger than steel, cracks under immense magnetic stress. These quakes release flares of gamma rays and X-rays that can be detected across the galaxy. In 2004, a magnetar 50,000 light-years away, in the constellation Sagittarius, unleashed a giant flare. For a tenth of a second, it released more energy than our sun has emitted in the last 100,000 years. This single blast of radiation, from halfway across the Milky Way, was powerful enough to ionize Earth's upper atmosphere, disrupting long-range radio communications and noticeably affecting our planet's magnetic field. It was a stark reminder that we live in a neighborhood where distant, exotic objects can reach out and touch us. The central mysteries surrounding magnetars are as profound as their power. How does such an intense magnetic field form in the first place? The leading theory is the dynamo model. It suggests that in the chaotic seconds after a supernova, as the neutron star's core collapses, a perfectly aligned convective soup of neutrons, protons, and electrons begins to spin with ferocious speed. This acts like a colossal cosmic generator, amplifying a pre-existing stellar magnetic field to magnetar levels in less than a second. But the details remain hotly debated. What drives their apocalyptic starquakes and giant flares? The star's unimaginably strong magnetic field is constantly trying to rearrange itself, exerting titanic forces on the rigid crust. This creates immense strain until the crust suddenly fractures, releasing pent-up magnetic energy in a flash. Think of it like bending a steel beam until it snaps, but on a scale where the beam is a star and the snap lights up the galaxy. These objects are more than just cosmic curiosities. They are natural laboratories for physics under conditions we could never hope to recreate on Earth. Studying them allows us to probe the behavior of matter at nuclear density, the limits of magnetic field strength, and the very nature of space-time under extreme distortion. Every flash from a magnetar is a message from the edge of physical possibility, a signal from a realm where the ordinary laws of nature are stretched to their breaking point. The titanic magnetic fields of magnetars bend reality itself, but they are not the only messengers from the abyss carrying impossible energy. Far above our atmosphere, the universe is firing bullets at us, particles moving so fast they carry the punch of a professional baseball, concentrated into a single subatomic speck. These are ultra-high-energy cosmic rays, and they represent one of the most enduring puzzles in modern astrophysics. A cosmic ray is not light. It is a physical particle, often a proton or an atomic nucleus, traveling through space at nearly the speed of light. The most common ones are low energy, streaming from our sun or other nearby stars. But the ultra-high energy ones are in a class of their own. A single one of these rare particles can carry the energy of a well-thrown fastball, millions of times more energy than we can produce in our largest particle accelerators like the Large Hadron Collider. When such a particle slams into Earth's upper atmosphere, it creates a spectacular air shower, a cascade of billions of secondary particles raining down over an area the size of a small town. The mystery is not that they exist, but how they got here. Physics tells us that a proton carrying that much energy is like a cosmic billiard ball on a very long, very crooked table. The universe is filled with a weak, tangled web of magnetic fields stretching between galaxies. A proton traveling across millions of light years should be deflected and scattered by these fields, bouncing around until it loses all sense of its original direction. By the time it reaches us, its path should be completely randomized, pointing back to nowhere. Yet, when we detect the very highest energy cosmic rays, a handful seem to point roughly toward possible sources. This should be impossible. It suggests either our understanding of particle physics at these energies is wrong, or these magnetic fields are far weaker in certain corridors of the universe than we believe. So what cosmic particle accelerator could possibly launch such a bullet on a straight enough path for us to notice? The suspects are all titans. The leading candidate is the active galactic nucleus, the supermassive black hole at the heart of a galaxy feasting on matter. As material swirls into the black hole's accretion disk, it becomes superheated and can launch jets of plasma at near light speed. These jets could act as a natural particle accelerator of unimaginable scale. Another possibility is the aftermath of a gamma-ray burst, the most energetic explosion since the Big Bang, which could blast out particles in a focused beam. More exotic theories involve the decay of super-heavy dark matter particles from the early universe, or defects in the very fabric of space-time called cosmic strings. The challenge is catching them, because these ultra-high-energy cosmic rays are so incredibly rare, striking a given square kilometer of Earth only about once per century. You need a detector the size of a small country. Scientists have met this challenge with ingenuity. The Pierre Auger Observatory in Argentina covers 3 square kilometers, an area the size of Rhode Island, with 1,600 water tanks spaced across the pampas. They wait for the faint flash of Cherenkov radiation when particles from an air shower zip through the purified water. Other experiments look for the faint ultraviolet light the air shower produces high in the atmosphere. Each detection is a precious data point, a clue from a particle that has traveled across the universe to deliver its message. The puzzle of their origin forces us to confront the most violent engines in existence, and to question whether the empty space between galaxies is as turbulent and magnetic as we assume. Every time one of these microscopic bullets hits our sky, it is a direct sample of astrophysical power at its absolute limit. Those microscopic bullets from the cosmos carry unimaginable energy, but they are fleeting sparks compared to the engine that drives the ultimate fate of everything. The destiny of the universe hinges entirely on the true nature of dark energy, that mysterious force accelerating the expansion of space itself. Right now, the most precise measurements we have paint a specific and deeply cold picture of our cosmic future. They point toward what cosmologists call the Big Freeze or heat death. In this scenario, dark energy remains constant or changes only very slowly. The acceleration continues, pushing galaxies apart at an ever-increasing rate. Over hundreds of billions of years, the universe outside our own local group of galaxies will redshift into invisibility. Star formation will gradually cease as galaxies run out of gas. Existing stars will burn out one by one until the last red dwarfs finally flicker into darkness. Black holes will slowly evaporate over incomprehensible timescales through Hawking radiation. The universe will become a vast, ever-expanding void, populated only by widely separated, dilute particles and a fading background glow approaching absolute zero. It is a quiet, lonely, and eternal end, but this forecast rests on a colossal assumption that dark energy is truly constant. We simply do not know that. What if dark energy is not a stable feature of the vacuum, but a dynamic field that can evolve? This opens the door to two other, far more dramatic finales. The first is the Big Crunch, a dramatic reversal of our current expansion. If dark energy were to weaken and eventually become attractive, the expansion of the universe could slow, halt, and then reverse. Galaxies would begin rushing back toward each other. The background temperature of the cosmos would rise as space compresses. Eventually, all matter and energy would be crushed together into an ultra-hot, ultra-dense singularity, a mirror of the Big Bang in reverse. It would be a cyclical universe, perhaps giving birth to a new cosmos in an endless cycle of expansion and contraction. The second possibility is far more violent and immediate. What if dark energy strengthens over time? This scenario is known as the Big Rip. In this model, the repulsive force of dark energy grows without bound. First, it would overcome the gravitational glue holding galaxy clusters together, flinging them apart. Then, it would rip apart individual galaxies. As the force intensifies, it would tear stars from their galaxies and planets from their stars. In the final moments, about an hour before the end of spacetime itself, the repulsive force would overcome the electromagnetic and nuclear forces that hold matter together. Planets, rocks, and even atoms and atomic nuclei would be violently shredded. The fabric of spacetime would be torn apart at every point. The universe would end not with a whimper, but with a catastrophic, fundamental disintegration of reality. Our current data from supernova and the cosmic microwave background most strongly supports the Big Freeze scenario. The measured acceleration appears consistent with a constant dark energy. But the margin of error in our measurements and the profound mystery of what dark energy actually is leaves the door wide open for a shocking twist. The ultimate fate of every galaxy, every star, every planet, and every atom is written in the language of a force we do not understand. It is the final and perhaps greatest mystery on the cosmic horizon, a question whose answer is encoded in the faint, accelerating drift of every point of light in the sky. The ultimate fate of the cosmos may be written in the unknown nature of dark energy, but a more immediate paradox threatens the very laws that allow us to write those equations at all. At the heart of this crisis lies a simple question with universe-shattering implications. What happens to the stuff that falls into a black hole? For decades, the answer from Einstein's theory of general relativity was grimly straightforward. It is gone. The immense gravity of a black hole crushes matter past the point of no return at the event horizon, dragging it down into a singularity, a point of infinite density where the laws of physics break down. According to relativity, a black hole can be described by just three simple features: its mass, its electric charge, and its spin. If you threw a grand piano, a library of encyclopedias, or a box of confetti into a black hole, the result would be identical. All the unique information about those objects, the arrangement of the piano's keys, the words in the books, the colors of the confetti, would be utterly and permanently erased from our universe. This presented no problem for classical physics, but in the 1970s, Stephen Hawking made a revolutionary discovery using quantum theory. He realized that the intense gravitational field just outside a black hole's event horizon should spontaneously create pairs of virtual particles. Normally, these particle pairs pop into existence and almost instantly annihilate each other. But at the edge of a black hole, one particle can fall in while its partner escapes, becoming real. To an outside observer, the black hole appears to be emitting a faint glow of radiation, now called Hawking radiation. This radiation carries away energy, which means the black hole slowly loses mass. Over aeons, a black hole will evaporate, fading away into nothing but this faint thermal haze. And here lies the paradox. Hawking radiation is purely thermal, like the heat from a stove. It contains no information about what fell into the black hole. So when the black hole evaporates completely, all the detailed information about every star, planet, or spaceship it ever consumed is lost forever. This violates a sacred principle of quantum mechanics, the law of unitarity. In the quantum world, information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. If you burn a book, the information in its letters seems lost, but a hypothetical superintelligence could, in theory, collect every particle of smoke and ash, trace every photon of light and heat, and reconstruct the entire book. Quantum mechanics demands this possibility. Black holes, according to Hawking's original calculation, are the one exception. They are cosmic shredders that destroy the quantum rulebook itself, creating what is known as the black hole information paradox. This is not a minor puzzle. It is a fundamental battle for the soul of physics, a direct conflict between the two pillars of modern science, general relativity and quantum mechanics. One of them must be wrong, or at least incomplete. The search for a solution has produced some of the most mind-bending ideas in theoretical physics. One leading proposal is the holographic principle. It suggests that all the information about the three-dimensional objects that fall into the black hole is not lost inside, but is instead encoded in a scrambled, two-dimensional form on the surface of the event horizon, like a cosmic fingerprint. The black hole's interior is a projection of that data, much like a three-dimensional hologram emerges from a flat, two-dimensional film. When the black hole evaporates, this information is slowly and chaotically released in the Hawking radiation, preserved but in a form we cannot yet decipher. A more radical and violent solution is the firewall hypothesis. It proposes that the event horizon is not a smooth, empty space, as relativity predicts, but a searing wall of high-energy particles. The instant you cross the horizon, you would be incinerated. This firewall would prevent information from ever falling into the black hole in the first place, resolving the paradox by dramatically altering our picture of the horizon itself. Yet this idea creates its own problems, violating Einstein's principle of equivalence, which states that falling through an event horizon should feel like floating in empty space. We are left with a cosmic detective story where the crime is the destruction of information, and the suspects are our most cherished theories. Solving this paradox will not just tell us what happens to lost matter, it will reveal the true, unified nature of space, time, and information at the most extreme frontier of reality. That battle between gravity and quantum mechanics at the edge of a black hole points to the single greatest unsolved problem in physics. Our universe is governed by two sets of rules that are fundamentally, spectacularly incompatible. On the vast stage of stars and galaxies, Einstein's theory of general relativity reigns supreme. It describes gravity not as a force, but as the curvature of spacetime itself, a smooth geometric fabric warped by mass and energy. This theory predicts black holes, the bending of light, and the expansion of the cosmos with breathtaking accuracy. Yet, in the microscopic realm of atoms and particles, the bizarre laws of quantum mechanics take over. Here, particles can be in two places at once, pop in and out of existence, and are connected by spooky action at a distance. The universe at this scale is not smooth, but grainy, probabilistic, and fundamentally uncertain. Both theories are magnificently successful in their own domains. The problem is, they cannot both be the final word, because our universe contains places where both sets of rules must apply simultaneously. The core of a black hole is a singularity of infinite density. The first instant of the Big Bang was a state of unimaginably small, hot density. In these extremes, the immense gravity described by general relativity meets the fuzzy, quantum world of the very small. Our equations blow up, physics breaks down. To describe reality at its most fundamental level, we need a single theory that seamlessly blends the two, a theory of quantum gravity. So why is gravity the stubborn outsider? In the standard model of particle physics, the other three fundamental forces, the electromagnetic force, the strong nuclear force, and the weak nuclear force, are all carried by specific particles. Photons carry the electromagnetic force, gluons carry the strong force, and the W and Z bosons carry the weak force. These particles are quantized, meaning they come in discrete, tiny packets of energy. For decades, physicists have searched for gravity's particle, the hypothetical graviton. The math suggests it should be a massless particle with a spin of 2, but here's the catch: gravity is astronomically weaker than the other forces. The gravitational attraction between two electrons is about 1 followed by 42 zeros times weaker than their electromagnetic repulsion. This incredible feebleness makes the graviton, if it exists, virtually impossible to detect with any particle collider we could ever build. More fundamentally, the mathematical language of smooth spacetime in general relativity simply refuses to mesh with the jittery, probabilistic framework of quantum field theory. When physicists try to force gravity into the quantum mold, their equations produce infinities that cannot be smoothed away, a sign that the theory is incomplete. The quest for quantum gravity has given rise to some of the most ambitious and mind-bending ideas in human thought. The most famous candidate is string theory. It proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny vibrating strings or membranes. The different vibrations of these strings correspond to different particles. One note might be an electron, another a photon, and a specific vibration would be the graviton. In this framework, gravity naturally emerges from the physics of strings, but string theory comes with staggering implications. It requires extra dimensions of space, not just the 3 we experience, but up to 10 or 11 in some versions. These extra dimensions are curled up into sizes so minute we cannot perceive them. Furthermore, string theory does not predict a single unique universe, but a vast landscape of perhaps 10 to the 500 possible universes, each with its own laws of physics. This leads to the controversial idea of the multiverse, where our cosmos is just one bubble in an infinite froth of realities. The primary criticism of string theory is its current untestability. The energy scales required to see the strings themselves are near those of the Big Bang, far beyond any conceivable experiment. The other major contender is loop quantum gravity. It takes a very different approach. Instead of adding extra dimensions, it tries to quantize spacetime itself. In this theory, space is not a smooth continuum, but a fabric woven from tiny, finite loops. Picture the universe as a vast network of these interconnected loops, a spin network. Volume and area come in discrete, indivisible units, a smallest possible piece of space, often called a Planck length. There is no such thing as a distance smaller than this. In loop quantum gravity, the smooth spacetime of general relativity emerges from this underlying quantum grain, much like a smooth piece of cloth emerges from woven threads. Black hole singularities are replaced by a quantum bounce, and the Big Bang might have been a big bounce from a previous universe. The challenge, again, is evidence. Probing the Planck scale directly is currently impossible. So how can we ever test these theories? Scientists look for subtle, indirect signatures. They search for minute changes in the speed of light of different energies coming from distant gamma-ray bursts, which could reveal the grainy structure of spacetime. They analyze the detailed pattern of the cosmic microwave background for imprints from the universe's first instant, a realm where quantum gravity would have held sway. Some even hope that future gravitational wave detectors might catch echoes from the quantum nature of black hole horizons. The mystery of quantum gravity is not just a technical problem for physicists. It is a search for the foundational language of reality, a single set of rules that can describe the cosmos from the first moment of time to the fate of a single atom falling into the abyss. Until we find it, our understanding of the universe remains beautifully, frustratingly, split in two. The search for quantum gravity reminds us that even our most cherished laws might bend under scrutiny, a lesson learned the hard way at the very edge of our own solar system. The Pioneer anomaly, that ghostly deceleration of 2 deep space probes, was a perfect example. For years, it stood as a tantalizing hint of new physics, a whisper that our understanding of gravity might be flawed. The resolution, as we saw, was a masterpiece of meticulous engineering, uneven heat radiation pushing back on the spacecraft. It was a humbling reminder that extraordinary claims require not just extraordinary evidence, but extraordinary elimination of the ordinary. Yet, the spirit of that anomaly, the hope of finding a loophole in the cosmic rulebook, found a new and controversial home in a small, strange device here on Earth. This is the story of the M drive, a concept that promised to revolutionize space travel and instead became a modern parable of scientific skepticism. The M drive, short for electromagnetic drive, was first proposed by engineer Roger Scheuer in the early 2000s. It was a radical idea, The device was a sealed, conical metal cavity. When you pumped microwaves into this cavity, bouncing them around inside, Scheuer claimed it produced a tiny but measurable net thrust in one direction. If true, it was nothing short of magic. It promised propulsion without propellant. A spacecraft equipped with an M drive would not need to carry and expel fuel. It could, in theory, accelerate continuously using only electrical power, perhaps from solar panels or a nuclear reactor, making interstellar travel a tangible possibility. The problem is, this seemed to blatantly violate Newton's third law of motion, the foundational principle that for every action, there is an equal and opposite reaction. Rockets work by throwing mass backwards to go forwards. The M drive claimed to generate forward thrust by bouncing photons around in a closed box, with nothing being expelled out the back. To physicists, this was akin to claiming you could move a car forward by sitting inside and pushing on the dashboard. The claims were met with intense and entirely appropriate skepticism. Yet, a few research groups, including a team at NASA Eagleworks Laboratory, reported they had built and tested their own versions. In vacuum chambers, they measured minuscule amounts of thrust, just micronewtons, the weight of a sesame seed on Earth. These results, though tiny, were enough to ignite a firestorm of public excitement and scientific debate. How could this be happening? The scientific community mobilized to find out. Teams around the world began constructing ever more precise experiments, designed not to prove the drive worked, but to root out any possible error. They considered and tested a long list of potential false signals. Could the thrust be from the magnetic interaction between the device and the Earth's magnetic field? They used magnetic shielding. Could it be from the heating of the device causing air currents in the vacuum chamber, even if the chamber was nearly empty? They improved their vacuum and modeled thermal effects. Could it be from the electrical wires supplying power to the device imparting a tiny force? They redesigned the tests. One by one, these potential errors were addressed. The most telling experiments came from teams in Germany and at the Technical University of Dresden. They built incredibly sensitive torsion balances and conducted tests with painstaking precision. What they found was decisive. The tiny thrust signal did not come from some new physics. It was an experimental artifact, a mirage created by thermal effects. As the microwave resonator heated up during operation, it expanded. This thermal expansion could cause subtle shifts in the device's center of mass or interact with the supporting structure of the test stand, creating a false thrust signal that perfectly mimicked what the M drive proponents were measuring. When these thermal effects were properly accounted for, the anomalous thrust disappeared. The door on the M drive, as a reactionless propulsion system, was closed. Like the Pioneer anomaly before it, the story is a powerful testament to the strength of the scientific process. An intriguing anomaly appears. It is investigated with initial excitement. Extraordinary claims are made. Then the rigorous, often unglamorous work of error hunting begins. In both cases, the answer was not a new force of nature, but a deeper understanding of the complex interplay between our instruments and the physical world. These episodes are not failures. They are the system working as it should, winnowing out wishful thinking and reinforcing the very laws that allow us to explore the cosmos in the first place. They remind us that the universe rarely gives up its secrets to a simple, elegant loophole, but instead challenges us to look deeper into the machinery of our own curiosity. The meticulous debunking of impossible engines like the M drive grounds us in the laws that govern our own backyard. But when we zoom out to the grand tapestry of the cosmos, we see those same laws playing out on a scale of breathtaking violence. Our own galaxy, the serene Milky Way spinning in the night sky, is not a peaceful island. It is a predator. Across billions of years, the Milky Way has been consuming its smaller neighbors in a process astronomers call galactic cannibalism. Gravity is the weapon. Dwarf galaxies, containing mere millions or billions of stars, wander too close to our galaxy's immense gravitational well. They are stretched, torn apart, and finally digested. The evidence is written in the sky around us. We can see the ghostly remains of these ancient meals as stellar streams, faint rivers of stars arcing across the galactic halo. These are the celestial equivalents of bones and sinew, the dismembered remains of galaxies long gone. The most famous is the Sagittarius dwarf spheroidal galaxy, caught in a death spiral around the Milky Way. Over time, it has been smeared into a great loop of stars encircling our own disk. Another, called the Gaia sausage, is the remnant of a massive dwarf galaxy that collided with the Milky Way perhaps 10 billion years ago, an impact so violent it may have puffed up our galaxy's central bulge. This cannibalism is not a rare event. It is how galaxies grow. Our Milky Way is currently in the process of devouring several smaller galaxies, and in about 4 billion years, it will engage in a monumental feast, a collision, and merger with the neighboring Andromeda galaxy. The two spirals will dance, warp, and finally coalesce into a single, giant elliptical galaxy. This is the brutal, beautiful ecology of the cosmic web, where growth comes from consumption. Yet, even as our galaxy feeds, it is itself being pulled. Our entire local group, including the Milky Way and Andromeda, is not drifting aimlessly. We are all racing toward a specific point in the distant cosmos at over 2 million kilometers per hour. The destination of this colossal migration is known as the Great Attractor. It is a gravitational anomaly of staggering proportions, a focal point in intergalactic space that seems to be drawing thousands of galaxies toward it. For decades, this was a profound mystery. The direction of this pull lies in the constellation Centaurus, but it is located directly behind the crowded, dusty plain of our own Milky Way. Our view is completely blocked by stars, gas, and dust, a cosmic blind spot called the zone of avoidance. We were being pulled towards something we could not see. What could possess enough gravity to tug on entire galaxy clusters? The first breakthrough came with the realization that the Great Attractor is not the final destination, but a waypoint. Our motion is part of an even larger flow toward an immense concentration of mass hundreds of millions of light years away, called the Shapley supercluster. But the Great Attractor itself is still a massive knot in the cosmic web. Modern surveys using infrared and X-ray telescopes, which can peer through the galactic dust, have finally revealed its nature. It is not a single, monstrous object. It is the heart of a colossal supercluster of galaxies, now called the Laniakea supercluster, which means immense heaven in Hawaiian. Our Milky Way resides on a remote filament of this vast structure, whose gravitational core is the Norma cluster. This region contains the mass of tens of thousands of galaxies, all bound together by their own gravity and, more importantly, by a deep well of dark matter. The Great Attractor is the center of gravity for our entire galactic neighborhood. It is the proof that the universe is not uniform. Matter clumps on the grandest scales, forming continent-sized structures with their own tides and currents, and we are floating down one of these immense rivers. The mystery has shifted from "what is it?" to understanding the detailed map of this dark matter landscape that guides the motion of everything we can see. These immense rivers of galaxies flow through a universe that is not just lumpy, but shockingly empty. The grand tapestry of the cosmic web is defined as much by what is absent as by what is present. Stretching between the dense filaments and clusters are regions of staggering nothingness, cosmic voids so vast they defy comprehension. The largest of these, like the Boötes void, span hundreds of millions of light years. If our Milky Way sat at the center of such a void, we would see only a handful of galaxies in our night sky, and the first human astronomers might never have guessed at the existence of other island universes at all. These are not perfect vacuums. They contain a few isolated dwarf galaxies and the faint, hot plasma of the missing baryons, but they are deserts on a scale that makes our local intergalactic space look crowded. Their existence is a direct prediction of our models of cosmic evolution. In the early universe, tiny quantum fluctuations were stretched by inflation. Regions with slightly more density pulled in more matter through gravity, growing into filaments and clusters. Regions with slightly less density were left behind, expanding into ever-growing empty bubbles as the universe stretched. The voids are the negative image of creation, the footprints of the primordial seeds of everything. Yet, their sheer size and emptiness raise their own subtle puzzles. Some voids appear too spherical and smooth, as if something prevented galaxies from forming there altogether. Studying the galaxies that do cling to life on the edges of these voids gives us a unique laboratory. How does a galaxy evolve in profound isolation, cut off from the constant interactions and mergers that shape those in clusters? The voids tell us that the universe's structure is a story of both congregation and evacuation, a balance between the dense knots of matter and these expanding bubbles of near-nothingness. If voids represent the empty stretches of the cosmic canvas, then ring galaxies are the universe's most delicate and puzzling brushstrokes. Floating in the darkness is an object of impossible perfection, Hoag's object. Discovered by astronomer Art Hoag in 1950, it is a nearly perfect ring of brilliant blue young stars, circling a central, older, yellow core of stars. Between the ring and the core lies a gap of profound, dark emptiness. It looks like a cosmic bullseye, a celestial smoke ring frozen in space. The most accepted explanation is as violent as the ring is serene. It is thought to be the result of a galactic collision, a smaller galaxy piercing the heart of a disk galaxy like our own Milky Way, head-on. The gravitational shock wave from this cosmic bullet would send a ripple of density through the target galaxy's disk, compressing gas and triggering a wave of star formation that propagates outward, leaving behind a perfect ring of newborn stars as the intruder galaxy is either destroyed or passes clean through. Computer simulations can produce rings that look very much like Hoag's object through this process. But the mystery deepens when we look closer. The central core of Hoag's object is almost perfectly round, not the elongated bulge we see in spiral galaxies. The ring itself is remarkably symmetrical and appears disconnected from the core, with no visible bridge of stars or dust. Furthermore, the ring's stars are all roughly the same age, suggesting a single, brief, and widespread burst of creation. Some ring galaxies, like the Cartwheel Galaxy, clearly show the aftermath of a violent collision with companion galaxies still nearby. Hoag's object, however, sits in solitary splendor, with no obvious culprit galaxy in sight. Could it have formed from a rare, stable configuration of matter after the Big Bang? Or is the collision theory still correct, with the intruder galaxy long since vanished, leaving behind only this exquisite fingerprint of its passage? Each perfect ring is a cosmic fossil of a single catastrophic moment, a snapshot of a galaxy rearranged by unimaginable force into a form of breathtaking and deeply mysterious beauty. These perfect rings and voids are the architecture of galaxies, but the true population of the cosmos may be something far darker and more solitary, drifting between the stars, invisible to our telescopes, are entire worlds without suns. These are rogue planets, orphaned worlds violently ejected from their young star systems by gravitational chaos. Picture an Earth or a Jupiter, not orbiting a warm sun, but sailing alone through the perpetual night of interstellar space. These are not theoretical, we have begun to find them. Using a technique called gravitational microlensing, astronomers watch for the telltale brightening of a distant star when an invisible rogue planet's gravity briefly bends and focuses its light like a lens. Each detection is a fleeting glimpse of a ghost. The numbers are staggering. Current estimates suggest there could be billions, even trillions, of these nomads in our galaxy alone, potentially outnumbering stars by a wide margin. They are the cosmic homeless, and their existence rewrites the story of planetary formation. We once pictured neat systems with planets orbiting in stable, clockwork harmony. The prevalence of rogue planets suggests that the early life of a star system is a violent gravitational pinball, where young giant planets scatter smaller siblings into the dark. The implications for life are chilling. A rogue planet would have no external source of light or heat. Its surface would be a global ice sheet, its atmosphere frozen solid. Yet there is a faint possibility. If such a world retained a thick hydrogen atmosphere or a hot radioactive core from its formation, it could trap enough geothermal heat to maintain a subsurface ocean of liquid water, locked under miles of ice. In the absolute dark, cut off from any star, life might cling to existence around hydrothermal vents, in a biosphere with no connection to the surface or the sky. Finding and studying these dark worlds is one of astronomy's greatest challenges, a hunt for shadows against a backdrop of black velvet. But there is a shadow of a different kind, one much closer to home, haunting the frozen fringe of our own solar system. Far beyond Neptune, in a region of icy debris called the Kuiper Belt, a handful of small objects are behaving very strangely. Their elongated orbits are clustered together, as if they are all being shepherded by the same unseen shepherd. Their paths are tilted, aligned in a way that should not happen by random chance. This peculiar orbital dance is the primary evidence for a hypothetical giant world, a super-Earth up to 10 times the mass of our own planet, lurking in the distant dark. Astronomers call it Planet 9. This is not the frantic search for a new planet in the classical sense. It is a forensic investigation. The clues are not in what we see, but in the patterns of what we have already found. The orbits of these distant objects are like breadcrumbs, pointing to the gravitational influence of something massive. The hypothetical Planet 9 would follow a wildly elliptical path, taking perhaps 10,000 to 20,000 years to complete a single, slow orbit around the Sun. Its average distance would be 20 times farther out than Neptune, placing it in a realm of perpetual twilight. The search is monumental. Its orbit is so vast that it could be almost anywhere along its billion-year journey. Telescopes like Subaru in Hawaii are methodically scanning the predicted swath of sky, looking for a single, faint point of light moving against the fixed background of stars. Finding it would be one of the greatest astronomical discoveries in a century, and it would force a complete rewrite of our solar system's history. How did such a large planet get there? It may have formed closer to the Sun and been flung outward by a gravitational tug of war with Jupiter or Saturn in the solar system's violent youth. Or, more tantalizingly, it could be a captured rogue planet, an interstellar orphan that our sun's gravity snatched as it drifted by. Either scenario reveals a solar system far more dynamic and chaotic than our textbook images suggest. The hunt for Planet 9 is a testament to the power of prediction. We are not just looking for a planet. We are testing the very limits of our understanding of gravity and planetary dynamics on the very edge of our own cosmic backyard. The hunt for a hidden world on the edge of our solar system forces us to question the very nature of reality. What if our cosmic horizon is not a boundary of space, but a boundary of existence? This brings us to the final and most profound mystery of all, a question that blends physics with philosophy. It is the simulation hypothesis, the idea that our entire universe, with all its galaxies, stars, and conscious beings, is not the base level of reality, but an artificial construct, a simulation running on some unfathomable computer in a higher realm. The argument begins with a simple assumption. If any civilization advances far enough, it would likely develop the capability to run vast, hyper-realistic simulations of its own history or of entirely fictional universes. Given the potential age and number of civilizations in the cosmos, there could be billions, even trillions, of such simulations running. If that is true, then simulated universes would vastly outnumber the one original base reality. Statistically, any conscious being, like you or me, is far more likely to be living inside one of the countless simulations than in that single, lonely original universe. It is a dizzying thought. Our entire lived experience, the feel of sunlight, the taste of food, the love for another person, could be lines of code in a cosmic program. But is this just a modern philosophical puzzle, or could we actually test it? Some scientists and thinkers argue we might look for glitches in the matrix, subtle signs of the underlying programming. One area of search is in the fundamental laws of physics. Our universe operates on mathematical rules that seem suspiciously clean and elegant, as if they were designed by a programmer who valued efficiency and consistency. The speed of light, the gravitational constant, the charge of an electron, these are the fixed parameters of our reality. Could they be evidence of a built-in architecture? More concretely, researchers have proposed looking for anomalies in high-energy cosmic rays. In any simulation, there is a limit to how much detail can be rendered, a finite resolution. If our universe is simulated, there might be a fundamental energy cutoff, a point where the simulation simply stops calculating finer details, which would show up as a sudden drop in the number of cosmic rays above a certain energy. So far, we have not seen such a cutoff. Others suggest that quantum mechanics itself, with its probabilistic, observer-dependent nature, bears a strange resemblance to a computer program that only renders reality in detail when someone is looking, to save processing power. The double-slit experiment, where particles behave as waves until measured, could be seen as a form of data optimization. The most famous proponent of this idea, philosopher Nick Bostrom, does not claim we are in a simulation. He simply argues that at least one of three propositions must be true. 1. Virtually all civilizations go extinct before reaching a post-human stage capable of running simulations. 2. Any such advanced civilization has zero interest in running ancestor simulations. Or 3. We are almost certainly living in a simulation. The hypothesis forces a confrontation with the deepest questions of consciousness and reality. If we are simulated, are our thoughts and feelings any less real? Does the programmer watch us, or is the simulation running autonomously? And what happens if we ever discover the proof? This mystery cannot be answered with a telescope or a particle accelerator alone. It lives at the intersection of our technological trajectory and our existential wonder. It is the ultimate horizon not of space, but of meaning. The 25 mysteries we have explored, from dark energy to dark matter, from cosmic voids to simulated realities, are not just puzzles to be solved. They are signposts. They point to a universe far stranger, more dynamic, and more mysterious than we ever dreamed. Each one represents a frontier of human curiosity, a place where our knowledge ends and the great unknown begins. They remind us that the cosmos is not a static backdrop, but an active, evolving story, and we are both its audience and its authors, peering out at the cosmic horizon and wondering what comes next. This ultimate horizon of meaning is mirrored by a physical one, a wall in the fabric of spacetime itself. The universe has a speed limit, the speed of light, and it is expanding. Combine these two facts, and you arrive at the cosmological horizon, the absolute boundary of the observable universe. It is not a physical barrier you could touch, but a frontier of information. Because space itself is stretching, there are distant galaxies receding from us faster than light can travel through the expanding space between us. Their light, carrying the story of their existence, is forever doomed to fall behind, never to reach our telescopes. We are surrounded by a sphere of ultimate ignorance, a horizon beyond which we can never see, no matter how powerful our instruments become. Every moment, as the expansion accelerates, more galaxies cross this threshold and vanish from our future view, lost to the cosmic dark. The observable universe is shrinking. What, then, lies beyond that final wall? One possibility is an infinite, eternal continuation of the cosmos we know. If the universe is flat and infinite, as our best measurements suggest, then beyond our horizon the patterns repeat. There could be regions so far away that an exact copy of our Milky Way galaxy exists, with a copy of our solar system and a copy of you watching this very video. In an infinite universe, every possible configuration of matter, no matter how improbable, must occur somewhere. The thought is both dizzying and lonely, a cosmos of endless echoes. Another, even more radical idea is that our universe is just one bubble in a frothing multiverse. The theory of eternal inflation suggests that the rapid expansion of the Big Bang never truly stopped everywhere. Instead, our entire cosmos is one stable bubble that formed in a still inflating, hyper-dimensional sea. Beyond our horizon could be an endless foam of other bubble universes, each with its own unique laws of physics. In some, gravity might be repulsive, atoms might never have formed, or time might flow backwards. We are trapped in our bubble, forever isolated from these alien realities by an expanse of inflating space we can never cross. Or perhaps the truth is something our brains are not equipped to fathom. The nature of whatever lies beyond the cosmic horizon might be as incomprehensible to us as a smartphone would be to a cave person. It could involve dimensions beyond our three, or a form of existence where concepts like space and time have no meaning at all. The cosmological horizon is the ultimate mystery wall, not because it hides something specific, but because it defines the limits of scientific inquiry itself. It is the final curtain, beyond which we can only speculate. Every mystery we have explored, from dark energy to quantum gravity, plays out within this finite stage. And that is the most profound realization of all. We are not just exploring the universe. We are exploring our tiny, shrinking share of it, forever wondering about the unseen immensity that lies just over the edge of everything we will ever know. That final wall of unknowable space frames our entire quest. We have journeyed from the invisible force tearing the cosmos apart to the silent matter holding galaxies together, from the profound silence of the Fermi paradox to the singular shout of the wow signal. We have chased phantom decelerations in our own solar system and witnessed cosmic firecrackers that outshine galaxies. We have puzzled over interstellar visitors with impossible shapes and confronted the stubborn absence of lithium forged in the universe's first moments. We have mapped a lopsided cosmos, measured a fundamental disagreement in its expansion, and finally found the missing atoms in a hot, dark web. We have stood before cosmic magnets that twist space-time, caught subatomic bullets from galactic accelerators, and pondered futures of frozen emptiness or catastrophic rips. We have grappled with information vanishing into black holes and the grand, unfinished battle to unite gravity with the quantum world. We have tested dreams of impossible engines and traced the flow of galaxies toward invisible attractors. We have admired perfect rings born from violence, hunted for orphaned worlds and hidden planets, and dared to question the very nature of our reality. These 25 mysteries are not a catalog of human failure. They are a map of human wonder. Each one represents a frontier where our knowledge ends, and where the next great discovery awaits. They are the unanswered questions that keep scientists awake at night, that fuel the design of new telescopes, and that send probes to the edge of our solar system and beyond. This is how science truly works, not as a set of fixed answers, but as an endless, thrilling conversation with the unknown. The universe is under no obligation to make sense to us, yet we persist in trying to understand it. That persistence is our greatest strength. So the next time you look up at the night sky, remember you are not just looking at points of light. You are looking at a vast, dynamic, and deeply mysterious story, and we are all a part of it. Stay curious. Follow the journeys of the James Webb Space Telescope as it peers at the first galaxies, or the Vera Rubin Observatory as it maps the dark sky. The next clue, the next piece of the puzzle, could be revealed at any moment. Which of these cosmic mysteries captures your imagination the most? Is it the chilling possibility of the great filter, the elegant violence of a magnetar, or the haunting idea of a simulated reality? Let us know in the comments below. And if you want to keep exploring the edges of understanding with us, be sure to subscribe. The horizon is vast, and the journey has only just begun.